In this video, we're going to cover indefinite integrals. So in the previous section, we discussed the idea of using rectangles to approximate the area between the function and the x-axis. The more rectangles, the better the approximation. Consider this notation, where A is the area of each rectangle in a region. The area of the region is the sum of the areas of the rectangles. Sigma is the Greek letter, which is the same as the S in our alphabet. They're the Roman alphabet. Okay, so here are the two different notations. The first one is our Greek notation, and this says, as the number of rectangles goes to infinity, as we get more and more rectangles, if we are adding up the areas, and this f of c sub k, that is the height of each of the rectangles, and then delta x, that is the base of the rectangle. And so each of these between these c values, this is just delta x. These are our the base of each rectangle. And of course, if we're looking at this diagram here, this would be like a right Riemann sum. And so this would be an overestimate, right? Because if this is concave down, it's not going to be exact. But as the number of rectangles increases and the base gets smaller and smaller, we are going to approximate the actual area. So this is our Roman notation. This is an integral sign, and we have a lower and an upper limit of integration. This is the integrand and the variable of integration. It represents the same thing. This f of x represents the height of each rectangle, and d of x, of course, is the base of our rectangles. So this is just simply a notation asking us to find the sum of the areas of the rectangles from some lower limit to an upper limit, a and b. The question now is, how do we actually calculate the sum to give the exact instead of an approximate? So here's a quick proof, and our task is to find the area between this curve, f of x, and the x-axis. When h is really small, we can consider the pink region a rectangle whose base is h, this guy right here, and the height is f of x. The pink area then is just f of x times h. Let a of x represent the green area under the curve between 0 and x, and a of x plus h represent the area of the green and the pink, so that would be all of this. The pink area can then also be found by subtracting the total area minus the area of the green. Therefore, the area of the pink and the green minus the green is equal to the height times the base when h is really small. Now, this yields the limit as h approaches 0. A of x plus h minus a of x equals f of x times h. If we divide both sides by h, hey, we know this to be the definition of the derivative. This is a prime of x. So this gives us the equation a prime of x is equal to f of x. The derivative of the region we are trying to find is equal to f of x. Equations will always stay balanced as long as you do the same thing to both sides. So if we take the antiderivative of both sides of the equation, and the antiderivative is just the reverse process of finding the derivative. The antiderivative of a prime of x is equal to the antiderivative of f of x. So a of x, which is the antiderivative of this guy, is equal to the antiderivative of f of x. So let's work through the process analytically now. All right, so just a reminder, when you're finding a derivative, you multiply the power by the coefficient, and you subtract 1 from the exponent. All right, so we're going to reverse these. When we find an antiderivative, we are going to add 1 to the exponent, and then we are going to divide by the power. Okay, so here's our first example. It's asking you to find the sum of the area of the rectangles between this curve, x squared, and the x-axis. Okay, so let's do it. If I want to find the antiderivative of x squared, I need to add 1 to the exponent, so that would be x cubed, and divide by the power. Now, when you're finding a derivative, let's go back one step. And you take the derivative of a constant, that goes to 0. So what we have to do is we don't know if this might have a constant attached to it, because if we take the derivative of this and there was a constant, well, then that constant would just go to 0. So in order to account for that, we've got to add a plus c. And this is called it's an arbitrary constant. It's known as the constant of integration. So we are always going to add a constant of integration. Whenever you don't have any other information, if we know the boundaries, then we can solve for that constant. But right now, we're just going to be adding a constant of integration to each of these. Okay, so let's try this next example. When I'm going to find the antiderivative of this one, I'm going to go ahead and rewrite it as 3x to the negative 2. Okay, so I'm going to add 1 to the exponent, and so that's going to give me 3x to the negative 1, and I'm going to divide by that power. And so I can rewrite this as negative 3x to the negative 1 plus c. If you wanted to, you could write it as negative 3 over x plus c. Either way would be fine. All right, in the next example, I'm going to go ahead and write this with a rational exponent. So 2 times x to the negative half. If I find the antiderivative of this, I would add 1 to the exponent. So that would give me 2x to the 1 half and divide by that power. And when you divide by a fraction, it's multiplying by the reciprocal, so that would give me 4x to the 1 half plus c, or if you wanted to write it 4 square root of x plus c, that would be appropriate as well. In the next example, okay, so if I think about this is x to the negative 1. If I add 1 to that exponent, now I have x to the 0, which is just 1, which is just not what I want. So think about your natural log. When we took the derivative of our natural log, that is 1 over x. So this guy, the antiderivative of this would be natural log. Now, it's natural log of x with absolute value bars because, of course, you can't evaluate a natural log of a negative number. So you do need to include the absolute value bars. And then we'll add the constant of integration. And then the last one, this is 6 over x. Again, that would give you x to the 0 if we added 1. So let's go ahead and use our natural log. And this would be 6 natural log, absolute value of x, plus c. Okay, a few more examples. Trig derivatives, of course. You got to think in the reverse. What's going to give you a derivative of cosine x? Well, that would be sine x. So this would just give you sine x plus c. And what gives you sine x as your derivative? Well, negative cosine x. Because remember, the derivative of cosine is negative sine. So if I want a double negative, I'm going to have to get a positive sign. Yeah, just make sure you are aware of that. All right, derivative of e to the x, well, that would just be e to the x plus c. Secant tangent, so let's see, that would be secant x plus c. Now this guy, in this next example, 1 over the antiderivative of 1 over 1 plus x squared. Think about your inverse trig derivatives, and this guy would be tangent inverse of x plus c. And the next one, sine inverse of x plus c. In this last example, there is another method, we're not there yet. So let's go ahead and expand this out and just apply the chain rule in reverse. So if I were to expand this, 2x plus 1 squared, that would give you 4x squared plus 4x plus 1. And if I take the antiderivative of that, let's just add 1 to each of the exponents. So that's going to give you 4x cubed over 3 plus 4x squared over 2 plus x plus c. And you could leave it like that, or you could clean it up just a little bit. you know, 4 over 2 would reduce to 2. All right, 2 more examples. My advice on this one, go ahead and separate each of those terms in the numerator over that common denominator. And so this is the integral from, or 3x cubed over 2x plus 2x over 2x minus 1 over 2x dx. And let's see, this would clean up just a little bit. 3 over 2x squared and dx. All right, so then I would go ahead and apply the integral to each of these terms. So the antiderivative of 3 over 2x squared plus the integral of 1. Oops, and I need to go ahead and, because these are areas of rectangles, I need to include the base, dx. Okay, and I should have probably put this all in parentheses, same with this guy. Because all of these guys, each of these is representing, well, this is representing the height, this is the base. If I separate them, I've got to find the height and the base of each of those terms. So, plus the integral of 1 dx minus, and let's see, I'm going to go ahead and pull this coefficient out front, the integral of x to the negative 1 dx. All right, and so if I find the antiderivative of this first guy, let's see, add 1 to the exponent. So that's 3 over 2x cubed over 3. Okay, that's going to get a little bit much, but it's okay. And the antiderivative of just 1, well, that's just x. And then the last one, and I wrote this 2 ways. I left the coefficient with the x term in this first term, and then in the second, in this third piece here, I pulled that coefficient out front. Either way is going to work just fine. Okay, so then this is just minus 1/2, and of course, if I add 1 here, that would go to 0, and so I know that this is my natural log. So this is going to be 1/2 ln of x. And then, of course, my constant of integration. I am going to clean up just this one little bit here because I don't want to have a fraction divided by a fraction. So if I multiply by the reciprocal, that's going to give me 1/2 x cubed plus x minus 1/2 ln absolute value of x plus c, and that one's done. All right, one last. In this example, we want to change from these. I want to go ahead and rewrite with rational exponents. So this would give me the integral of 3x to the 3/4 plus 7x to the negative 5 plus, how about 1/6 x to the negative 1/2 dx. Okay, so I'm going to go ahead and just find the antiderivative of each of these. So I'm going to add 1 to the exponent. So this would give you 3x 3/4 plus 4/4 would give you 7/4. Add 1 to this exponent. Add 1 to this exponent. So that's 1/6 x to the positive 1/2 divided by 1/2 plus c. And I'm going to go ahead and clean this up just a little bit. If I divide by a fraction, it's the same thing as multiplying by the reciprocal. So I'm going to multiply by 4 over 7. So that's going to give you 12 over 7 x to the 7/4. Here, I'm just going to go ahead and move the negative, not move the 4. 7 over 4x to the 4th. And then multiply by the reciprocal, so that's going to give you 2 over 6 is 1 over 3, x to the 1/2 plus c. And if I wanted, I could write this as the square root of x, but I think I'm pretty good. All right, guys, it is now time to practice.